Hello, everyone, and welcome to Episode 3 of our Automotive Cybersecurity Engineering series. I'm Jack Huang, and today we're diving into one of the most critical topics in modern automotive security vehicle architecture evolution. Over my 25 years in this industry, I've watched these architectures transform from simple distributed systems to the sophisticated software-defined vehicles we're building today. This evolution isn't just about technology. It's fundamentally about security. Let's get started. Before we begin, let me tell you what you'll walk away with today. First, you'll understand the three main vehicle architecture types. And trust me, knowing these is absolutely essential for your career in automotive cybersecurity. Second, you'll be able to explain why the entire industry is evolving from distributed to zonal architecture. This isn't just a trend, it's a necessity driven by security and cost. Third, you'll identify the security strengths and weaknesses of each architecture type. This is where we separate good engineers from great ones. Fourth, you'll recognize software-defined vehicle trends. SDVs are not the future, they're happening right now. And finally, you'll understand real-world implementations from Mercedes, Volkswagen, GM, and BYD. These aren't theoretical concepts. These are billion-dollar investments happening as we speak. Ready? Let's dive in. Let me start with the big picture. Vehicle architecture has evolved through three distinct generations. Think of it like this: if you look at a vehicle from the 1990s, then a vehicle from 2015, and then a cutting-edge 2025 electric vehicle, you're looking at three completely different electronic architectures. Generation 1 is what we call distributed architecture. Picture this 70 to 100 individual ECUs, each doing one specific job. Function-specific means one ECU controls your wipers, another controls your door locks, another controls your engine. The wiring? It's incredibly complex. We're talking about 1.5 kilometers of cable weighing over 50 kilograms. And here's the security problem: weak isolation. Your infotainment system could be sitting on the same bus as your brakes. That's terrifying from a security perspective. Generation 2 is domain-centralized architecture, and this is what most vehicles on the road today use. Here we consolidate those 70 ECUs into maybe 30 to 50 more powerful domain controllers. You have a powertrain domain, a chassis domain, a body domain, an infotainment domain. They're connected through a central gateway. Much better isolation, but still complex. And Generation 3, this is where we're heading, is zonal architecture. Instead of organizing by function, we organize by physical location. Front left zone, rear right zone, cabin zone. Each zone has a controller that manages everything in that physical area. The result? 25 to 30% less wiring. A central computer acts as the vehicle's brain. This is the foundation of software-defined vehicles. This evolution isn't arbitrary. Each step was driven by real problems: cost, weight, complexity, and most importantly, for us, security. Let's start with where we came from: distributed architecture. I call this the legacy approach, and here's why. In the characteristics box on the left, you see function-specific ECUs. What does this mean in practice? It means if you wanted to add cruise control to a car, you literally installed a new physical ECU just for that feature. Want adaptive headlights? Another ECU. Every single feature required its own hardware. 70 to 100 plus ECUs per vehicle. Modern luxury vehicles from this era could have over 100 individual computers. Think about that for a moment. Managing, updating, and securing 100 separate computers in a moving vehicle. Direct point-to-point connections created wiring nightmares. I've personally seen wiring harnesses that took days to install and were so complex that if one wire failed, troubleshooting was nearly impossible. Now, look at the security weaknesses on the right. This is where things get really problematic. Weak domain separation. In the famous 2015 Jeep Cherokee hack, and I'll tell you about this in a moment, the researchers found the infotainment system and the brake ECU on the same CAN bus. No separation whatsoever. Multiple attack paths. With so many ECUs and so many connections, an attacker has dozens of potential entry points into critical systems. OBD directly connected. The OBD2 port that mechanics use for diagnostics. In distributed architectures, it often connected directly to critical vehicle networks. That's like leaving a backdoor unlocked and difficult to update and patch. There was no centralized update mechanism. If you needed to patch a security vulnerability, the vehicle had to come into a dealer, and each ECU had to be updated individually. Now, the famous example at the bottom. In 2015, security researchers Charlie Miller and Chris Velasek remotely hacked a Jeep Cherokee. They compromised the infotainment system through a cellular connection, and because there was no isolation, they jumped directly onto the CAN bus where the brake ECU was sitting. They could control the brakes, the steering, everything. This resulted in a recall of 1.4 million vehicles. This wasn't theoretical. This was real. And it changed everything about how we think about vehicle architecture and security. So the industry responded with Generation 2 domain centralized architecture. This is what I like to call grouping by function with a security guard at the door. Let's look at the key features on the left. Domain control units, or DCUs. Instead of having 10 separate ECUs for your powertrain, you consolidate them into one powerful domain control unit. Same thing for chassis, body, infotainment, and ADAS. This immediately reduces complexity. Well-defined domains. We clearly separate powertrain from chassis, from body, from infotainment. Each domain has its own network. Central gateway. And this is the game changer. The CGW sits in the middle and routes traffic between domains. More importantly, it filters that traffic. It enforces rules like the infotainment domain cannot send messages to the chassis domain. Ethernet backbone for high-speed communication between domains. We're talking gigabit speeds instead of the 1 megabit of CAN. Now look at the security improvements in the green box. Physical domain separation. The infotainment network is literally a different physical network than the chassis network. An attacker who compromises infotainment can't just jump directly to the brakes anymore. Gateway filtering. The CGW acts like a firewall, enforcing access control rules. This is huge. Intrusion detection becomes possible. Because all traffic flows through the gateway, we can monitor it for anomalies. Centralized OTA updates. We can now push updates to multiple ECUs through the gateway without requiring a dealer visit. But, and there's always a but, look at the remaining challenges in yellow. Gateway complexity and cost. A good central gateway is expensive and complex to develop. Still 30 to 50 plus ECUs per vehicle. We've reduced the count, but it's still a lot. DCUs require hardware and software isolation. Running multiple applications on one powerful processor creates new security challenges. And here's the big one. The gateway is now a single point of failure. If an attacker compromises the gateway, they can potentially access everything. It's become the most valuable target in the vehicle. This is the architecture most vehicles use today. It's good, but we can do better. And that brings us to Generation 3 zone architecture. This is a complete paradigm shift, and I want you to really understand this. Look at the paradigm shift box at the top. Traditional domain architecture says group all the powertrain ECUs together, all the body ECUs together, regardless of where they are in the vehicle. Zone architecture says forget about function. Group everything by physical location. Everything in the front left corner of the vehicle, headlights, radar, door locks, window motors, all connects to the front left zone controller. Everything in the rear right connects to the rear right zone controller. Why is this brilliant? Let me explain with the two boxes at the bottom. Zone controllers manage local sensors and actuators in their zone. They handle power distribution right there locally. They process data locally when possible. No need to send every sensor reading to a central computer. And this reduces wiring by 25 to 30%. Think about what that means: less weight, less cost, less complexity. But zone controllers are not the brains. They're more like the nervous system. The central computer is the brain. It's a high-performance vehicle computer that runs the core software defining vehicle behavior. It makes high-level decisions like, we need to brake now, or activate lane keeping. The zone controllers execute those decisions. This is the architecture that enables true software-defined vehicles. The hardware becomes a platform, and software defines what the vehicle can do. Mercedes is doing this. Volkswagen and Rivian are partnering on this. Tesla has been doing a version of this for years. This is not the future, this is now. Let me walk you through the 6 key benefits of zonal architecture, because these are compelling. First, reduced wiring complexity. Traditional vehicles have 1.5 kilometers of wiring weighing over 50 kilograms. Zonal architecture cuts this by 25 to 30%. That's significant weight and cost savings. Second, lower manufacturing cost. Simpler assembly, less copper, fewer ECUs to install and test. When you're manufacturing millions of vehicles, these savings multiply fast. Third, enhanced OTA updates. This is huge! You can update multiple domains in a single OTA session. Want to enable a new feature? It's just software. No hardware change needed. BMW is already doing this. They sell features as subscriptions that you can activate over the air. Fourth, better diagnostics and maintenance. Standardized diagnostic interfaces and easier fault isolation by zone. When something fails, you know exactly which zone to look at. Fifth, improved EV range. For electric vehicles, every kilogram matters. Less wiring means less weight, which means less energy consumption, which means more range. This is critical for EVs. And sixth, faster feature deployment. You can add new features via software updates, not hardware changes. Want to deploy an improved AI algorithm for your ADAS system? Push it to the fleet in real time. No dealer visit required. Traditional automotive development cycles were measured in years. With zonal SDV architecture, you can deploy new features in weeks. This flexibility is why every major OEM is investing billions in this transformation. Now let's talk about what really matters to us: security. Zonal architecture is a double-edged sword. Look at the security advantages in the green box on the left. Unified security framework. The central computer manages security policies for the entire vehicle. One place to define and enforce security rules. Better update coverage. You can patch multiple domains simultaneously. When a vulnerability is discovered, you can fix it across the entire vehicle in one OTA update. Enhanced monitoring. Centralized intrusion detection. One security operations center monitoring all vehicle activity. Simplified key management. Fewer nodes means fewer keys to manage. In a distributed architecture, managing cryptographic keys for 100 ECUs is a nightmare. Managing keys for 15 zone controllers and one central computer? Much easier. But now look at the security risks in the red box on the right. Single point of failure. If an attacker compromises the central computer, they potentially affect all zones. This is the all your eggs in one basket problem. Gateway as high-value target. All data flows through the central gateway. That makes it the most valuable target for an attacker. Software complexity. More complex software means a larger attack surface. More lines of code means more potential vulnerabilities. Dependency on connectivity. Heavy reliance on cloud and OTA. If your update mechanism is compromised, you could push malicious updates to millions of vehicles. So what do we do? Look at the security best practices at the bottom. Redundancy. Deploy dual central computers or failover mechanisms. If one fails or is compromised, the other takes over. Hardware security modules. Protect your cryptographic keys and secure hardware that can't be extracted even if the system is compromised. Secure boot and attestation. Verify software integrity before execution. Make sure you're running authentic, unmodified code. Runtime protection. Use hypervisor isolation to separate different applications, memory protection to prevent unauthorized access, and intrusion detection to catch attacks in progress. The bottom line: zonal architecture offers security advantages, but only if implemented correctly. The stakes are higher, so our security controls must be stronger. Let me show you some numbers that prove this isn't just theory. This is happening right now. Look at the zonal ECU market growth on the left. In 2024, it's worth $2.15 billion. By 2033, it's projected to hit $11.41 billion. That's a compound annual growth rate of 18.7%. That's massive growth. Zone controller units specifically, on the right, are growing even faster. From $3.2 billion in 2023 to $18.6 billion by 2030, CAGR of 29.7%. Nearly 30% annual growth. The industry adoption forecast approximately 40% of new vehicles will use zonal architecture by 2034. That's less than 10 years away. Almost half of all new cars. The total EE architecture market, everything we're talking about, grows from $79.4 billion in 2024 to $148.6 billion by 2034. Nearly double. Now read the key insight at the bottom carefully. The automotive industry is in the midst of a massive architectural transformation. Zonal and SDV are not future concepts. They're happening now. Premium segments like Mercedes, BMW, and Tesla are leading. They can afford the R&D investment, and their customers expect cutting-edge technology. Mass market segments will follow by 2027-2028. Once the technology is proven in premium vehicles, it cascades down to mainstream vehicles. If you're an engineer starting your career today, zonal and SDV architecture will be the standard by the time you're mid-career. This is what you need to know. Let me show you real examples. These aren't concepts. These are actual programs with actual budgets happening right now. Mercedes-Benz MB, OS, 1.3 billion euros invested. Zone-based design. They're achieving 30% wiring reduction. Production starts in 2025, that's this year. Volkswagen Cariot, over 2 billion euros in software platform investment. Their ID family of electric vehicles already uses a centralized architecture. And in November 2024, they formed a joint venture with Rivian, investing up to $5.8 billion by 2027 to develop zonal SDV architecture. General Motors Ultifi, $2.3 billion for SDV architecture development in 2023-2024. They're building a service-oriented platform with full SOA. Stellantis STLA Brain, 4.5 billion euros in multi-year investment. This will be their cross-brand SDV platform used across all Stellantis brands. Baidishwanji Architecture. They're transitioning from domain-centric to zonal, integrating cloud AI with vehicle edge AI. Neoskyos. AI-first strategy from day one. They're using a world model for scenario simulation that launched in 2025. And the note at the bottom, all major OEMs, Toyota, BMW, Ford, Hyundai, have announced similar initiatives for 2025 to 2028. This is billions of dollars in investment, thousands of engineers. This is the industry's future. So let's talk about the ultimate goal software-defined vehicles, or SDVs. What is an SDV? Read the definition carefully. A vehicle where primary value and functionality are driven by software rather than hardware. Features can be added, modified, or upgraded through software updates without changing physical components. Think about your smartphone. When Apple releases iOS updates, your iPhone gets new features without changing the hardware. SDVs bring this same concept to vehicles. Look at the key SDV characteristics on the left. Centralized computing. One powerful vehicle brain instead of distributed ECUs. Service-oriented architecture. Software is built as decoupled services communicating via standardized APIs. This enables flexibility and reuse. Continuous OTA updates. Regular software updates just like your smartphone gets. Extensive cloud connectivity. The vehicle constantly exchanges data with the cloud. Hardware abstraction. The software is independent of the underlying hardware. You can upgrade the hardware without rewriting all the software. Now the benefits on the right, and these are why every OEM wants SDVs. New revenue models. Sell features as subscriptions. Pay-per-use models. This transforms the business model from one-time sales to recurring revenue. Faster innovation. Deploy new features in weeks instead of years. The traditional automotive development cycle of 3 to 5 years becomes obsolete. Personalization. Use AI to customize the driving experience for each individual user. Lower recall costs. When there's a problem, fix it with an OTA update instead of bringing millions of vehicles into dealers. Extended vehicle lifecycle. Keep vehicles technologically current for 10 or more years through software updates. This is why the software-defined vehicle market is projected to grow from $213 billion in 2024 to over $1.2 trillion by 2030. It's not just about technology, it's about business transformation. Let's bring it all together with a comprehensive comparison table. Look across the rows and really understand the progression. Number of ECUs 70 to 100 in distributed, 30 to 50 in domain centralized. Only 10 to 20 in zonal. We're reducing complexity dramatically. Wiring 1.5 kilometers in distributed, 1.2 kilometers in domain, only 1 kilometer in zonal. That's 30% less. Architecture philosophy function-based, then domain-based, then location-based. Gateway local gateways everywhere, then central gateway, then zone controllers plus central. Domain isolation weak, then good, then excellent. OTA updates difficult, then moderate, then easy and comprehensive. Manufacturing cost high, then medium, then lower. Security strategy ECU level hardening, then gateway filtering, then central plus zone defense. Main risk weak isolation for distributed. Gateway complexity for domain. Single point of failure for zonal. Timeline legacy before 2015. Current from 2015 to 2025. Future from 2025 onward. This table tells the story of where we've been, where we are, and where we're going. Memorize this progression. Let's wrap up with the 5 key takeaways you need to remember. Number 1. The industry is evolving from distributed to domain centralized to zonal architecture. This is a clear progression driven by real needs. Number 2, distributed architecture. The legacy approach has weak security isolation and complex wiring. It worked for its time, but its time has passed. Number 3, domain centralized architecture, the current standard, provides better isolation via the central gateway. Most vehicles on the road today use this approach. Number 4, zonal architecture, the future, reduces wiring by 25 to 30% and enables true software-defined vehicles. This is where the industry is heading. Number 5, major OEMs like Mercedes, Volkswagen, and GM are investing billions in SDV transformation. This is happening now, not in some distant future. If you take nothing else from this presentation, remember these 5 points. They form the foundation of modern automotive architecture. Let me close with a look ahead what to expect in the next 5 years. Fully centralized computing. We're moving toward a single vehicle brain handling all functions, with zone controllers acting as simple data aggregators. Edge AI processing. Low latency AI decision-making at the edge is critical for autonomous driving safety. You can't send sensor data to the cloud and wait for a response when you need to break in milliseconds. Cross-zone sensor fusion. Seamless data sharing across all zones will enhance both safety and comfort. A camera in the front left zone will share data with the rear right zone in real time. AI-driven predictive maintenance. Vehicles will predict failures before they happen, learning from fleet-wide data to optimize performance. Standardization and consolidation. By 2028, we expect 3 to 5 dominant SDV platforms, similar to how the smartphone market consolidated to iOS and Android. And cybersecurity as a core requirement. Security by design from day one. It's no longer optional. It's mandatory for regulatory compliance under UN R155 and similar regulations worldwide. The next 5 years will see more change in vehicle architecture than the previous 20 years. It's an exciting time to be in this field. Thank you for your attention today. I hope this gives you a clear understanding of vehicle architecture evolution and its security implications. If you have questions, reach out to me at jackwang0210gmail.com. Up next is Episode 4, where we'll dive into the threat landscape and attack vectors. That's where we'll explore how attackers actually exploit these architectures. Until then, keep learning, and remember architecture is the foundation of security. Get the architecture wrong, and no amount of security controls will save you. Thank you.